Welcome to Team 3 of Cal Poly Pomona's class of Orbital Mechanics, ARO 3090, Section 4's presentation on the Orbital Path Trade Study for Voyager 3.
The 3 Mission Development Team comprises of Thomas Normandow as Team Lead, Jackie Tran as Team Deputy, Adam Von Dudang, and myself, Trevor Noakes, as part of the High Thrust Subteam, as well as Nate Falkenberg and Jared Ludwig as part of the Low Thrust Subteam. During this presentation, we will be covering the technical analysis for the Voyager 3 mission. The parameters for the mission will be outlined, as well as various analyses performed to design the mission. These include trajectory analysis, launch vehicle analysis, observation target analysis, as well as the orbital propulsion system analysis.
Many great insights into our solar system were provided by Voyager 1 and 2. Voyager 3 hopes to continue these achievements by going beyond our solar system and viewing exoplanets with the use of solar gravitational lensing. This uses the sun's gravity to bend light and focus it into our own telescopes. However, this will require the satellite to be 550 AU away from the sun, placing it outside of the solar system.
Launching from Earth between the year 2035 and the year 2050, the spacecraft would perform 2 flybys with Venus and 1 flyby with Earth before transiting towards Jupiter, where the spacecraft would perform an off-Earth maneuver or a powered flyby to obtain as much velocity as possible to escape the solar system. The trajectory were based off idealized two-body trajectories. For instance, the models we used were patch conic sections where we treated the sun as our central body and patched together our conic trajectories via the iterative Lambert method to determine our series of flybys. For our flyby of Jupiter, we assumed the Albert impulse was instantaneous at the parapsis of the flyby path, and we treated our final targets as static points, seeing that the trajectory for real stars can be off by a couple of arc minutes depending on our time of flight.
The trajectory selected was derived from the Cassini-Huygens mission profile, which utilized a high-thrust propulsion system. Trajectory analysis and date selection was carried out through the use of MATLAB and simulation accomplished in FreeFlyer, which you will see towards the end of this presentation.
For this mission, we chose the SLS, as it has good specific impulse both in sea level and vacuum conditions, and it can take up to 50 tons into orbit. It has 2 stages. The first stage has 2 solid rocket boosters from Northrop Grumman, and a cryogenic core stage that utilizes 4 Aerojet Rocketdyne RS-25 engines. As for the second stage, it consists of 4 RL-10 engines and its propulsion tanks. And the second stage also houses and carries the payload, which is the spacecraft, and the spacecraft's propulsion system.
The trade studies the team had performed were the selection of the final spacecraft destination between the TRAPPIST-1 and the Wolf 1061 systems, between low-thrust versus high-thrust spacecraft.
Analysis of both our targets, we see that TRAPPIST is very much in line with the ecliptic, making it a very efficient target. It also has 7 observable planets, 3 of which are potentially habitable. However, tidal locking decreases the probability of this. Both host stars are red dwarfs, TRAPPIST being less massive, which decreases the orbital period of its planets, and due to highly active electromagnetic events, any atmosphere around the planets in the TRAPPIST system would likely be scorched away. We see that the orientation is important as TRAPPIST's planets transit its host star, allowing for potential atmospheric spectroscopy with the James Webb Space Telescope once that gets up and running, versus the Wolf 1061, which is only detected by radial velocity, which increases the uncertainty with regards to its local ecliptic. Wolf 1061 also is moving away from our ecliptic in terms of its mean proper motion at about a rate of 1.2 arc seconds per year, which would have to be accounted for any sort of trajectory that is performed. TRAPPIST is, though, further away, which increases our optical limitations as diffraction fundamentally limits.
The observation target selected is the TRAPPIST system, with the 3 planets in its habitable zone, observable transits, and a particularly active red dwarf star makes this system a fascinating target for study. The James Webb Space Telescope would provide spectral data for scientific analysis prior to the Voyager 3 mission that will use the gravitational lensing for a direct observation of the TRAPPIST system.
For our mission, we end up analyzing low thrust maneuvering versus high thrust maneuvering. Ultimately, end up picking high thrust maneuvering due to the fact that it provides quick impulse burns, which allows us to achieve a high enough acceleration relatively quickly. This also allows us to couple our flybys with an overth burn. This overth burn is important because when we reach Jupiter, it allows us to achieve a high enough speed to reach our destination, which is 550 AU, relatively quickly. We were also able to model our trajectory in FreeFlyer, which allowed us to complete a simulation of our full mission.
High thrust propulsion system on this mission, we chose to go with a pressure fed system, as it is the simplest way to create thrust. We will have a cluster of 8 Ariane Group 400 Newton chemical monopropellant thrusters. This was the route chosen as hydrazine is easier to store compared to hypergolic propellants, and it stays liquid in room temperature. And also, it can last for years. Lastly, it has a pretty good decent ISP of 220 seconds.
This slide shows the Jupiter pork chop plots clocked in after January 1st, 2035, and it is the departure date versus time of flight days for direct trajectory to Jupiter with a max C3 of 100. The minimum C3 that this will give us is 75 kilometers squared per second squared, which gives an orbit mass of 14,000 kilograms using SLS. This will severely limit the amount of propellant that we can use and giving us a very small amount of the infinity to work with for the different maneuvers. And it's mainly just showing that going straight to Jupiter was impractical and there were better options for us to use. Our first rendezvous with Venus in days after January 1st, 2035. Ultimately, ended up picking Venus because it allows us to have a significantly lower C3 cost compared to if we had a direct trajectory to Jupiter. As you can see by the ARO, we ultimately picked a date that allows us to reach our rendezvous with Venus in 187 days. This is an analysis of the high thrust overth burn that our spacecraft will need to complete in order for it to reach its intended destination. As the spacecraft reaches Jupiter, it will need to complete an impulse burn at perigee. This graph shows the viable delta V changes that our spacecraft will need to make as it reaches Jupiter. The top part of this curve shows when Jupiter is at a position that is less than ideal in order for us to make the maneuver, while the lower part of the curve represents when Jupiter is basically at a position that allows a tangential impulse. So the delta V change we ended up selecting was a 6.869 kilometers per second, and then a time of flight of approximately 88 years in order to reach destination.
Design of our trajectory using a C3 of 15.75 for our insertion to Venus. We use an on-orbit mass of 39,000 kilograms with a burn at perigee with a delta V of 6.87 kilometers per second using 37,000 kilograms of hydrazine. This amounts to a 7.2-hour burn, which we model as being instantaneous. Total time of flight is 88 years, which is slightly longer than the half-life of plutonium-238, which is used in the RTGs. We have a final mass of 1768 kilograms, which is delivered to the observation point. On this slide, you'll see the animation for our modeled trajectory, which is the Earth to Venus to Earth to Jupiter-powered flyby. Our turn angles are determined by the inbound and outbound V infinities compared against minimum allowable altitudes, and this of course gives us our increase in heliocentric velocity. The animation is quite long, though if you skip to the end, which you can skip in the slides as I'm narrating, you'll see that TRAPPIST, modeled as a large red star, is quite in line with the Sun, allowing for active usage of gravitational lensing. If you click
To meet mission objectives, we will be viewing TRAPPIST-1, using a high-thrust propulsion to reach the desired destination. The initial Earth launch will use a NASA Space Launch System Block 2, and by using flybys, we will reach our target in 88 years.
If you're watching, everything after this is just a rundown of my code. You don't have to watch that, but thank you. So this is really just a quick overview of the code used to determine our orbits. This isn't essentially part of our presentation. It is, however, acts as sort of additional information should you need to see how our calculations worked out. You'll see that we load in our, on the far left, you'll see that we load in our ephemeride data, which gives us planetary locations and velocities, which is what's used to patch together our Lamberts. The code, of course, has comparisons for time of flight given each event, V infinities. We see our C3 determination for our initial launches, as well as turn angle calculations compared against planetary gravitational constants and minimum allowable radii. All in all, this code runs for quite some time as it's a series of nested for loops with fairly high search resolution, but the outputs are text documents that allow further analysis for each state. This doesn't necessarily outline the entirety of the code used. It does outline important subblocks. On the left, you'll see the method for connecting valid Jupiter trajectories, which were determined in our previous slide with the previous code, to trajectories that get us to TRAPPIST-1 observation points, which of course takes into account the Oberth maneuver we perform, which is an increase in our delta V at perigove. We put constraints as a maximum of 20 kilometers per second, which isn't really something that can be attained, but it's good for the graphs to have that data. And of course, we have our minimum radii for our perigove, which is also used for determination of valid flights.